So we're interested in categorical syllogisms, which of course are composed of categorical propositions. And we've mentioned that categorical propositions relate categories to one another in one way or another, right? And that means we can use Venn diagrams to give us a visual representation of what it is that we are committing ourselves given a particular categorical proposition. And the reason why Venn diagrams can do this is because we can represent categories as circles. So if you're the category, if we're talking about the category of lizards, for instance, so let A for the moment be the category of lizards. Then anything that is a lizard falls somewhere in this circle. And if we let the category B be reptiles, then anything that is a reptile falls in with this circle. And we've made it so that the circles overlap. And by having them overlap, then we can use two further symbols from the modern standpoint. There's also going to be a traditional standpoint, but right now we're going to focus on the modern standpoint. There is shading, which is like erasing an area, because it says that nothing exists there. And then there's X's, which is like saying that there's at least one thing that exists in an area. So given this Venn diagram, we have three areas. The one that's outside of both A and B. These are non-A's and non-B's. The area that is in A but outside of B. The area that is within both A and B. And the area that is in B but outside of A. Well, we happen to know that all lizards are reptiles. So if we want to give ourselves a visualization of that categorical proposition that all lizards are reptiles, then we have to get rid of the area. That is, we have to shade the area where you have lizards, but they're not within the reptile category. Because what that does is that leaves the only A's left over to be within this area. And if you look then, if there is an A, it has to be a B. Because if there is an A, the only place left over to put it is in area 3, which are also B's. So all of our lizards, all of our A's are B's, even though that's not true of our B's. I mean, going in the other direction, it's not the case that all B's are A's. But instead of a universal claim, we might have a particular claim. So we might say some lizards are reptiles, in which case we're saying there's at least one thing that's both a lizard and a reptile. Well, being that that's what we're asserting, then what we would do is take an X, since that represents at least one thing existing, and we would put it in the area that makes it this thing, this at least one thing, both a lizard and a reptile. All right, so those are the basics to Venn diagramming from the modern standpoint. And what we're going to do now is we're going to look at how the four categorical propositions, how we represent those visually, the four standard cases of categorical propositions, how we represent those from the modern standpoint using Venn diagrams. So first, let's take a look at A propositions. And A propositions take the form of all A are B. And remember that what we're saying when we say that all A are B is if members of A exist, then they're also members of B. That's for any A, right? For any member of A, if such a thing exists, it's also going to be a member of B. So if we have area 1, 2, 3, and 4, we notice that if something were to exist in 2, then it would be an A that is not a B, because it's outside of the B categories, outside of the B circle. Well, that violates what all A are B says. So in order to represent visually what all A are B commits us to, we have to get rid of area 2. Now all of our A's, the only A's that are left over, are within the B circle. And so this shows that all A's are B's. Next we have our E proposition, no A are B. And remember, this tells us that if members of A exist, then for any of those members, they are not also a member of B. So what we're saying then is that our categories of A and B are completely separate from each other. They're excluded from one another. Well, if we look at 3 is the area in which A and B are not excluded from one another. So in order, and that violates what this means, that violates what no A or B says. So in order to visually represent what no A or B says, we have to get rid of area 3. We have to shade it out. And now we can see that area 2, which is the only A's that are left, in area 4, which is the only area in which B's are left, they are completely separated from one another. There's no overlap. So anything that ends up being an A, it will not be a B, and anything that ends up being a B will not be an A. Now let's look at I statements. Some A are B. Some A are B commits us to there being at least one thing that belongs to the A category. So there's at least one member of A, and it's also a member of B. Well, it's not telling me to put the X in area 1 because those are neither A's nor B's. It doesn't tell me to put the X in 2 because those are A's that are not B's. They are outside of the B circle, the B category. And it does not tell me to put the X in 4, area 4, because those are B's that are not A's. We need our X to be both an A and a B. So by putting an X in area 3, we've committed ourselves to the existence of one thing that is both an A or B, that is, some A or B. For our I statements, our O statements rather, they say that some A are not B. Well, we still commit ourselves to the existence of an A, so there's one member of A, but it is not a member of B. Well, again, I can't put my X in area 1 because those are non-A's and non-B's. I can't put my X in 3 because this says there's one member of A that is not a B, but to put an X in 3 would be to commit myself to something as both an A and a B, but that's not what our categorical proposition says. And I can't put an X in area 4 because that would be to commit myself to the existence of a B that is not an A. But what I've committed myself to is the existence of an A that is not a B. So I need to put it in area 2. 2, it's an A, but the area 2 is outside of our category of B. So this is an A that is not a B. The standard cases of categorical propositions are relatively easy to diagram with the Venn diagrams. But things can get to be a little bit more tricky when we introduce the notion of complementary classes, and also when we deny that a categorical proposition is true. But for the moment, let's look at complementary classes. What is a complementary class? Well, as an example, if we have the class A or the category A, its complementary class is non-A. Likewise, the complementary class of non-A is A. But let's take a look at where our non-A's are. So if we want to deal with the complementary class of A's, we need to be, and we're worried about diagramming, we need to be worried about where the non-A's exist. And let's use this. Let's let non-A's, our symbol for non-A's, be this, an A with a line on top. In that case, we have non-A's in 1 because it's completely outside of the A circle. So everything that exists in area 1 is a non-A. But not only are they in 1, notice that area 4 is also outside of 2 and 3, the place where we have A's. So 4 is where we also have non-A's. So we have non-A's in both 1 and 4. So if I said that all non-A's are B's, then the only place where we can have non-A's that are B's is 4. And since all of our non-A's are B's, that means I would have to get rid of 1. So I would shade out area 1. Like so. And this now visually represents that all non-A's are B's, because the only non-A's that are left over are in 4, and 4 is entirely within the category of B. The other thing that can make Venn diagrams a little bit more challenging is when we deny the categorical proposition. That is, when we say the categorical proposition is false. So if we have, for instance, the categorical proposition that all A are B, but we tack it is false that in front of it, so it is false that all A are B, what we do is we think about where we would shade, and then instead of shading, because we're saying it's false, we put an X there. So we've already seen that where we would normally shade all A are B is in area 2. All A are B. This gets rid of area 2. And by getting rid of area 2, we would make everything that is in A that is B. But what we're actually saying, though, is that this is false. And for it to be false is for there to be at least one thing that is A and not a B, right? If it's false that all A are B, what makes that false is that there exists one thing that's an A that's not a B. So instead of shading in this area, shading in area 2, we should put an X. So we would normally shade out that area, but since we put it is false that in front of it, in front of the categorical proposition all A are B, we put an X. So now let's think about if we had the proposition some A are B. Only we're tacking it is false that in front of it. Well, when we think about how we would normally diagram just the proposition some A are B, we would put an X in the third area. Because now that the X commits us to there being at least one thing that exists, and it exists in both the category of A and the category of B, which means it's both an A and a B. So some A are B. But we're saying that's false. And to say that it's false that there's something that's both an A and a B is to say that there isn't anything that is both an A and a B. A and B as categories are completely separate from one another. So instead of putting an X in the area, in the third area, in fact, what we need to do is shade it. And that represents it is false that some A are B. So again, the main point is you first think about how you would diagram the categorical proposition without it is false that in front of it, without the denial of it. And then wherever you would shade, you would put an X. And wherever you would X, you would shade. You just do the other thing. So for your notes, I want to give you a decision procedure for Venn diagramming from the Boolean standpoint. And what I recommend to first do is, given the categorical proposition that you have, label the classes that are in play so that you can visualize which areas you're going to be concerned with. So for instance, let's say you have the following categorical proposition. It's all A are non-B. Then what we need to do is we need to think about the areas that we have with Venn diagrams. So let this be our A circle and let this be our B circle, our B category. And since we're saying that all A's are B's, area 2 is one that we might be interested in because we're interested in A's, as well as area 3, since area 2 and 3 is where our A's are located. But then we might also be interested in area 1 since it's a non-B. But notice we're doubly interested in area 2 because that's also where our non-B's are. So area 2, we should be paying attention to area 1, 2, and 3, but we should be paying especially close attention to area 2. Now in our second step, we want to determine whether we're going to be shading or Xing. Since we're dealing with a universal proposition, we know we're going to be shading. If we were dealing with a particular proposition, one that begins with some, then we know that we would be Xing. In our third step, we want to determine where we would shade or X the diagram to make the standard form proposition to be true. And what I mean here is a proposition that does not have it is false that in front of it. So which area would you put your X? What area would you put your shading? So again, if we have all A are non-B, everything that is an A is a non-B, we're going to end up having to get rid of area 3. Because that's where we have A's that are B's, but we've said that all of our A's are non-B's, which is why we needed to pay a special attention to 2, because that's where our A's and non-B's are, and those are the only things that can exist based on the statement that all A's are non-B's. Then once you figured that out in the standard form, if it is in standard form, that is, it does not have it is false that in front of it, then you just do what you determined in the third step. You either put an X there or you shade it out. So we had to shade out 3, area 3. But if the proposition was not in standard form, if it did have it is false that in front of it, then instead of actually putting a shading in area 3 like we did, we would instead put an X. Roughly like so. So that's if it were to have it is false that in front of all A are non-B. All right, so let's take a look at how Venn diagramming can help us determine whether an argument is valid or invalid. So if we have the proposition all non-P are non-S, and we want to see if that guarantees the truth of it is false that some S are non-P, we can use Venn diagrams to show that this argument is in fact valid. Notice that it's not obvious if you're just trying to think about those propositions intuitively. It's not obvious whether the conclusion follows from the premise. But let's take a look to see why it does. If we have area 1, 2, 3, and 4, and we say all non-P are non-S, we first need to figure out what areas are in play. Well, we have non-P's in area 1 and in area 2, because those are the areas that are outside of the P circle. We then have non-S's in area 4 and in area 1, because those are outside of the S circle. So then we think about what we're saying when we say that all non-P, everything that's a non-P, is a non-S. Well, if we look at area 2, what we notice is those are non-Ps that are S's, and that violates the claim that all non-Ps are non-S's. They need to not be S's. So we have to get rid of area 2. Now let's think of the conclusion. First, what we do is we bracket off it is false that, just so that we can look at the standard form of the proposition. Some S are non-P. We have area 1, area 2, area 3, and area 4. We're going to be worried about S's, so we're going to be worried about area 2 and area 3. We're also worried about non-P's, so we're worried about area 1, and we're worried about area 2 yet again. And still ignoring it is false that, so just looking at some S are non-P, we see that we would put an X in area 2, because that would commit us to the existence of an S that is a non-P. But then we take off our brackets of it is false that, and we remember that we do the opposite of what we would normally do. So instead of putting an X in area 2, we shade it out. And notice that what our Venn diagrams then show us is that these mean exactly the same thing. It wasn't clear that they do, but now we see that it does. So since they mean the same thing, it's clear that the conclusion does in fact follow from the premise. Now that we have a pretty good handle on how to diagram Venn diagrams from the Boolean or modern standpoint, we should talk about existential import. And in doing so, let's first look at the arguments that I have here. On the left, the argument says all A are B, therefore some A are B. The argument on the right says no A are B, therefore some A are not B. Ask yourself whether you think these arguments are valid or invalid. I'll give you a little time to make that decision. Okay, so it turns out this is a little bit of a trick question, because whether the argument is valid or invalid depends on the interpretation that you take, the standpoint that you take. If we take the Boolean or modern standpoint, then both of these arguments are invalid and they commit what's called the existential fallacy. And the reason for this is that on the Boolean standpoint or modern standpoint, neither of these premises have existential import. That is, they do not commit us to the existence of the things that are in the subject term place. So they do not commit us to the existence of, in this case, they do not commit us to the existence of A's. And why is that? Well, if you'll remember from the Boolean standpoint, we said that all A are B, what it says or what it commits us to is if A's exist, if there are A's, then they are also B's. But because the question of whether A's exist is within that if statement, if A's exist, we're not actually committing ourselves to A's existing. So it turns out that our premise 1 here on the left can be true if there are no A's, if A's don't exist. The same sort of thing is happening on the argument on the right. When we say no A or B on the Boolean or modern standpoint, what we're saying is if A's exist, if there is an A that exists, then it is not a B. It will not also be a B. Since the question of A's existence is within that if statement, we're not committed to A's actually existing. So one way for the premise on the right side to be true is if A's do not in fact exist. And if we are presented with a situation, a circumstance, a possible circumstance in which A's don't exist, then our premises will end up being true, but our conclusions will be false. And the conclusions will be false because our particular statements, the statements that begin with some, do commit us to the existence, in the cases that we're looking at, they do commit us to the existence of A's, because they get interpreted as some A are B, there exists an A and it's also a B. Some A are not B, there exists an A and it is not a B. So our particular statements do have existential import. But that means the premises can be true but the conclusion is false. A valid argument is one that if the premises are true, then the conclusion cannot be false. So these instances violate that definition and they are therefore invalid. and we say they commit the existential fallacy. Now things are different if we take the traditional Aristotelian standpoint. And before we know the subject matter that we're talking about, we say these arguments are conditionally valid. We say that they're conditionally valid because their validity depends on the condition of whether the thing in the subject term refers to an actual object that exists. So up here, if our A's do exist, so they refer maybe to dogs, cats, people, whatever, then it has existential import. On that condition, on the condition that it refers to existing things, it has existential import, and therefore does commit us to the existence of the things on the Aristotelian traditional standpoint. And since it commits us to the existence of those, then because these are true, it will have to be that there exists at least one thing that's an A, that's a B given this premise, or given this premise, there'll have to be something that is an A and is not a B. But if that condition is not met, because the things that we are referring to do not exist, so rather it refers to these unicorns or elves or gnomes or whatnot, then these will turn out to be true for the same reason that we were given for the Boolean or modern standpoint, but the conclusion will end up being false. And so again, if it doesn't meet that condition, even though the arguments are conditionally valid, if we then look to see what A refers to, and it refers to non-existing things, then at that point, we will be able to say that it's invalid and commits the existential fallacy. Now we're going to turn our attention to the modern square of opposition, or the Boolean square of opposition. And the point of the square of opposition is to inform us how our categorical propositions, the different kinds of categorical propositions, relate to one another. And there's going to be two types of relationships that we're interested in. One is logical equivalence. And we say that two propositions that necessarily always share the same truth value are logically equivalent propositions. So if they always have to share the same truth value, then they are logically equivalent. The other relationship that we're interested in is contradictions, or logically contradictory. So if of two propositions, when one is true, the other is necessarily false and vice versa, then they are logically contradictory. So let's take a look at the modern square of opposition to see how it can help us identify when the categorical propositions are either logically equivalent or when they're logically contradictory. So what we have here in this diagram is our modern or Boolean square of opposition, and the relationship that it informs us of is contradictories. So it tells us that A and O are contradictories, and it tells us that I and E are contradictories. And since these are contradictories with each other, they must have the opposite truth value. So if we have the A proposition, all S are P, and we plug in T for that A proposition, that means if we keep the subject term and the predicate term uniform, and then the O proposition of it must be false. And vice versa. If we plug in false here, it's got to be true up here. Likewise, if we plug in true for our O proposition, then our A proposition has to be false. If we plug up false up here, then our O proposition has to be true. And the same thing's going to happen with our E and I propositions. If it's true that no S are P, then it's got to be false that some S are P. And if it's false that some S are P, it's got to be true that no S are P. And if it's true that some S are P, it's got to be false that no S are P. And if we plug in the false up here, then we've got to get the T down here. So our Boolean square of opposition tells us that these propositions are contradictory. And we can actually see this by making Venn diagrams. So if we have all S are P, then we need to shade out area 2. And if some S are not P, then we're committed to there existing an S that's outside of the P circle. And the only place to put that is in area 2. But this diagram tells us that nothing can exist in area 2. So nothing's supposed to exist here. And this tells us that there's at least one thing that exists here. Well, you can't have it both ways. So if this is true, this has to be false. And if this is true, this has to be false. That's why they're contradictory. Now notice we can introduce it is false that. So it is false that in front of one of these statements. And then what we get instead of contradictories is we'll get logical equivalent propositions. Because when we say it is false that all S are P, we first think about how we would diagram all S are P. And as we said, we would shade out area 2. But then because it says it is false that in front of it, we would do the opposite. And that's just what some S are not P tell us to do, to put an X in area 2. So these propositions have the exact same meaning, and they'll be true in all the same cases, and they'll be false in all the same cases. What this means then is that adding it is false that or denying a categorical proposition can make for hidden kinds of propositions. So if we have an E proposition such as no non-G are F, we can see that we would diagram it in the following way, where this is our G's, this is our F's. Then we have non-G's in area 1, we have non-G's in area 4. And we say that none of our non-G's are F's, which means we would have to get rid of area 4. And if we say it is false that some non-G are F, and we want to diagram that, then first we look at some non-G are F, here is a non-G's. They're in area 1 and they're in area 4. And to say that some non-G are F would be to say that there exists at least one non-G that is an F. So if that's all we were diagramming, we would put an X in area 4. But then we recall that, oh yeah, we're saying it's false at, so we have to do the opposite of putting an X. And so we shade out area 4. So really, it is false that some non-G are F really is the same thing as an E proposition. It just doesn't look like it. And we can show the same thing by using the square of opposition instead of Venn diagrams. So we get rid of these Venn diagrams, and then we construct for ourselves a square of opposition. Our A propositions up here, O propositions down here, our E propositions down here, and our I propositions down here. Now, we've already said that these are contradictory, so our premise is asserting that no non-G are F, and no non-G are F takes the form of an E proposition. So it's asserting that this E proposition is true. What our conclusion asserts is it is false that some non-G are F. Well, if we think about some non-G are F, that will be the I proposition that is uniform. Its subject term and predicate term are uniform to the premises. So it's going to be false. It's going to get the truth value of false if E gets the truth value of true. But notice that that's just what this conclusion says. It says that it is false that some non-G are F, which means that the whole conclusion is right. It's correct in saying that the I proposition is false, given the premise that the E proposition is true. So again, these propositions are going to have the same truth value. They're logically equivalent, which is why it's a hidden E proposition. It really is an E proposition, even though it doesn't look like it.